Okay, guys. Yeah. Let's talk about significant digits. Okay, it's not going to take very long, right? But we got to kind of go over how we determine how many significant digits our answer should have. Okay, so first thing, how many people have heard of significant digits before? Awesome, this is going to be really easy then. Okay, what's the purpose of significant digits? Why do we worry about them? Why are they so significant? Because of the name? Yeah? Partly.
They tell us what we need to round to.
Okay, they tell us what we need to round to.
Gives an answer that's somewhat relevant to the questions units.
Exactly. It gives us an answer that essentially preserves or is relevant to the measurements given to us in the question. Okay? Basically, they ensure that I don't take two numbers that are measured to a certain degree of accuracy and come up with an answer that's suddenly more accurate than the numbers I actually measured. Okay? I can't increase the accuracy of my numbers by doing math with them. Okay? Accuracy is determined by measurement. Once that measurement is done, I can only be that accurate. But if I combine two numbers that are of differing accuracies, my answer, whatever I get by combining those, if I'm adding them or dividing them or whatever, has to reflect the accuracy of my least accurate measured value. Okay, so when I'm done a question, if I've done a whole bunch of math throughout a whole question, at the end of it I have to go, okay, my least accurate measured value was this accurate. Therefore my answer can only be that accurate. Okay, even if I used a bunch of other numbers that were more accurate than that, I can only be as accurate as my least accurate measured value. Everybody got me there? Okay. So, how do I tell if a number is significant? How many significant digits are in that number?
Nope.
What you put up first was right, because you went like this, and then you went, oh, and then you weren't sure anymore.
Oh, it's that.
It's this.
This one.
Okay? There are 5 numbers there, right? Would I have written any of those numbers if they weren't measured? I shouldn't. Okay? So every one of those is a measured value. Okay? Anything that's not a 0, we assume to be significant. Okay? I wouldn't write it if I didn't measure it. 0 is the number that gives us trouble. Sometimes 0 is significant, and sometimes it's not. Okay? So, here's a situation that you could come across. How many significant digits does that number have? 3. Okay? That number has 3 significant digits. Place holding zeros are not measured. There was nothing here to measure. Okay? The number is smaller than those values. Okay? Therefore, those numbers are not significant. Okay? So leading zeros are never significant. Okay? Leading zeros are never significant digits. Okay? How many significant digits does that number have? 5. Okay? I wouldn't have written those numbers if they weren't important. Okay? There may not have been anything there to measure, but I'm certain that there wasn't anything there to measure. Okay? So trailing zeros are always significant. Okay? That's the thing we have to remember. Leading zeros, never. Trailing zeros, always significant. Think of it this way. If it would go in scientific notation, it's significant. Right? So when I look at this number here, if I'm going to put it in scientific notation, it would be 1.23 times 10 to the minus 3. Okay? If I put this number in scientific notation, it would be 1.2300 times 10 to the 4. Okay? I would include those zeros, the trailing zeros, but not the leading zeros. Okay? Everybody with me there? Okay. Anything that's not a 0, always significant. Leading zeros, never significant. Trailing zeros, always significant. Okay? All right. Now the rules around the math. Okay. if I have to add or subtract numbers, then I go by decimal places or positions for accuracy. So if, for example, I had my final answer would only go to what decimal place? The tenths position. Okay, that's as accurate as I measured. My least accurate number was only measured to the tenths position. Therefore, my answer can never be more accurate than that. Okay, everybody all right with that idea? Same goes for subtraction. Okay, if I'm multiplying and dividing, the rule is easier. Okay, with multiplying and dividing, if I take 1.23456 and I multiply that by 5.2, how many significant digits can my answer have? 2. Okay, if I'm multiplying or dividing, my answer has the same number of significant digits as my least accurate number. That's 2. Okay, my least accurate number there is 5.2. Okay, it has 2 significant digits. My answer would have 2 significant digits. Okay, regardless of decimal places. Okay, if I'm multiplying or dividing, I just look at my numbers and go, okay, that one has 3, that one has 4, that one has 2, my answer has 2. Done. In fact, that rule works about 98% of the time. Okay? Because most of the time, we're going to be doing problems that involve more than one operation. And as soon as you have more than one operation, you're just going by your least accurate number. Okay? Everyone all right with that? All right. Sometimes, do questions play dirty tricks on you and give you a number you don't use? Okay. If you don't use that number, does it affect your accuracy? That's the one trick to watch for. Okay? Sometimes the question will do that on purpose to test your significant digits. Okay? They'll give you one number, it's your least accurate number, but you never use it for anything. Okay? And if that's the case, you got to go with the next one. Okay, for your significant digits. So if I had givens like this, let's say that I was given a final velocity of 1.5 meters per second, an initial velocity of negative 2.3, 2.3. That's close. These always break when they fall. Okay, 2.34, okay, and okay, let's say a question gives me those numbers, but when I'm done the question, I've never used D. How many significant digits should my answer have? 2. Okay? If I don't use D, the fact that it only had one significant digit does not affect my accuracy. So I go with the next least accurate number, which is 1.5. And that only has 2 significant digits, so my answer would have 2. All right? Everybody okay with that? Okay. Last weird rule with significant digits. Measured versus counted. If you count something, is that the same as measuring it? It's not. Okay? So, if I count the number of people in this room and I find that there are 25 people in this room, how certain am I of that? 100% certain. I counted you. There are 25 of you. There's probably more than that, but let's just say it's 25. Okay? Then I'm certain there's 25. That's not a measured value. Therefore, it does not affect my significant digits. Okay? It doesn't happen often, it doesn't come up often until like unit 4, where you might be counting the number of times a pendulum oscillates. Okay, so if you count that it oscillated 4 times, that 4 only has, well, appears to only have one significant digit, but in fact, it's infinitely accurate because you didn't measure it, you counted it. Okay, everyone following me on that? We'll cover that again when we get to that unit. It comes up again so rarely that really only needs to be important in unit 4. Okay? All right, everybody good with sig these? Like I said, 98% of the time, it's write down your givens and go with the least accurate number. Okay, every once in a while, you get a question that plays a dirty trick on you and you gotta watch for it. Okay. All right. Point values and stuff on quizzes. Okay, so if we were looking at these here, I had one that was out of 5 and one that was out of 3. Okay, just so you know, if the person has the right answer, they get all 3 marks if it's out of 3. Okay, if they got the right answer, it's out of 5, they get 5 marks. Okay. But you should still show your work. Okay, because the steps are important. And if, you know, by some act of God, you accidentally type it into your calculator incorrectly, and all you write down is a number that's wrong, I can't give you anything for that. Okay? It's better to have all of your work written down. I can go, oh, that person's just really clumsy with their calculator, but they knew how to do it. They get 4 out of 5. Okay? Does everyone follow me there? Okay? I've had this argument with students in the past, and it always ends badly for them. Okay? Because I had a kid who never showed any work, ever. And I argued with him constantly about it. I said, I don't need to show my work, Coder. I can just do it in my head. I'm like, that's awesome, good for you. But, you know, if you're not showing your work and you're just punching it all into the calculator and you do something wrong, you're gonna get nothing for that question. Yeah, that's fine, I'm not gonna make that mistake. Final exam, reset his calculator, he didn't put it back in degree mode. Okay, any question that involved having to use trigonometry, he got wrong. Okay, because he didn't show me any work and his calculator was in the wrong mode. Now, he really should have noticed that his answers made no sense, but he didn't, because he didn't show any work and he didn't understand why his answer didn't make any sense. Okay, so the moral of the story is show your work. The secondary moral is Coder is always right. Probably not true, but okay, yeah. Okay, let's look at acceleration. Okay, that's going to be our next thing. We've done all the graphing stuff now. Okay, so we're going to do acceleration today and tomorrow, and then Thursday we'll do our lab with the carts and the Chromebooks and all of that stuff. Okay. Okay, so accelerated motion, or the idea or concept of acceleration, should be familiar to you. We have talked about acceleration in Science 10. Okay, we did some simple calculations of acceleration in Science 10. All that's going to change in Physics 20 is we're going to add 4 more acceleration formulas. Okay, you only had 1 acceleration formula in Science 10. We're going to add some more. Okay, gives you better ability to solve acceleration problems. Okay, so first key point: what is accelerated motion? Okay, well, we've defined that I don't know how many times over the last few days. If something is changing its velocity, it's accelerating. Any change in velocity over time is an acceleration. Okay, positive, negative, doesn't matter. Any change in velocity is accelerated motion. Okay, we're going to look at the relationship between change in velocity, distance, time, and acceleration. That's basically how our formulas work. Okay, and I'm going to refer back to velocity time graphs several times today. Okay, and be able to solve accelerated motion problems with all of the formulas that we cover. Okay, so if you take out your formula sheet and just look at the kinematics section of it, okay, that's the first kind of block there on that front page, you will see a number of formulas that contain acceleration. Okay. You'll see the good old Science 10 one, A equals delta V over delta T. Oh, sorry, yeah, delta V over delta T. Okay, and then you'll see a few other ones that have A in them. They may not be A equals, but they'll say there's A in them. Those are our other acceleration formulas, and they can help us solve for initial velocity, final velocity, time, displacement, okay, all of those good things. So that's what we'll be looking at today. Okay, so the definition of acceleration is anytime the velocity of an object is changing, the object is considered to be accelerating. Okay? So we're going to be dealing with mostly uniform acceleration, okay? Simply because that makes the better kind of graphs and things like that we can deal with. Okay? And uniform acceleration is like best exemplified by either an object that's falling or a plane taking off. Okay? But a lot of people go, well, Mr. Coder, why not a car accelerating away from a stoplight? Okay? Well, a car accelerating from a stoplight does accelerate, obviously, but it's not very uniform. Why?
I think we're gonna have to like change gear.
Yeah, it has to change gears. Okay, even in electric cars, I mean, they're gonna have a bit more of a uniform acceleration, but it's still not gonna be perfect. Okay, and the reason for that is the faster you go, the more wind resistance there is, so the more forces that are opposing your acceleration, okay, and it starts to kind of flatten out. So, if I'm looking at something that's accelerating uniformly, its velocity versus time graph is gonna look like this. And it's gonna be just a diagonal line. Okay, the amount it changes its velocity by is exactly the same every time interval. That's uniform. A car accelerating away from a stoplight is a graph that looks like this. Okay, it accelerates really well at first. Okay, but especially if it's a car that has a transmission and is shifting gears, that curve starts to flatten as it increases in speed. Okay, and of course then you've got all the additional forces of air resistance and stuff like that going up as it goes faster, which also reduces its acceleration. Okay, does anyone here drive a manual standard transmission? Okay, that number goes down every time I ask that question, getting fewer and fewer. So if you drive a manual transmission, you know that if you want to pass somebody on the highway, you don't stay in like 6th or 5th to do it. Okay? Because that gear provides you insufficient acceleration to get around that vehicle and back in your lane. Okay? If you drive an automatic and you stomp on the gas, you can hear the transmission shifting gears down to give you additional acceleration from the lower gears, okay, and giving you that steeper part of the curve. Okay? If you drive a standard transmission and you stay in 6th, you're going to be trying to accelerate around the vehicle with that part of the curve. That's not good. That will equal bad things happening. Okay, so you would want the car to shift, or shift it yourself if it's a manual, down to a gear where the curve is steeper. Okay, everybody all right with that idea? Okay. Okay, so let's look at a simple example of what you would have done in Science 10. Okay, so this would have been a Science 10 question. It says, the plane in this picture starts from rest. All right, that's an important term for us to know, and you probably got introduced to it in Science 10. If something is at rest, it is not moving. Okay, so if something starts from rest, VI, initial velocity, is 0. If it comes to rest, then its final velocity is 0. If it comes to rest. Okay, rest always means 0, but starts from rest, initially 0, comes to rest, finally 0. Okay, so this one starts from rest, so we know one of our givens is VI. Okay, and the plane accelerates down the runway, and at time 29 seconds, so they tell me this thing's going to accelerate for 29 seconds, okay, it attains a velocity of positive 72.2 meters per second. Okay, determine the average acceleration of the plane. Okay, so looking at my formula sheet there, which formula should I use to solve this problem? Tris?
VF minus VI over T.
Exactly, this one. Acceleration equals VF minus VI over T. It's the only formula I have everything for. Okay, I have VF, I have VI, I have T, and I'm looking for A. All right, so definitely that's the formula I would want to use. And lucky for me, I don't even have to manipulate it. It's already set up to solve for acceleration. So all I have to do is plug in my numbers. 72.2 minus 0 divided by 29 seconds. Okay. All right, so the acceleration of that plane is 2.5 meters per second squared. Positive. Okay, is that ringing a bell from last year? Where does that formula come from? comes from a velocity versus time graph. What does it calculate besides acceleration on that graph? Okay, a graph of this plane would look like this. What part of that graph is acceleration? The slope. Okay? B is how fast it's going at time 0, which is 0 because it was at rest. Okay? VF would be y, time would be x. Okay? That leaves m as the slope. If I was solving for m, it would be y minus b over x. That's VF minus VI over t. Okay, that's what we talked about yesterday. All right, that formula comes from the slope of a velocity versus time graph. Come on. Okay, so that's the work we just did there. Okay, we get positive 2.5 meters per second squared. So what that means is every second that plane is going how much faster? Somebody said it. 2.5 meters per second. Okay, every second that plane is going to be going 2.5 meters per second faster than it was the second before. Okay. All right. So these are your other acceleration formulas that we're going to use. Okay, you don't have to write them down because they're on your formula sheet. Okay, but these are the other 4 acceleration formulas. Okay, now these two are also derived from your velocity versus time graph. Okay, and I'll show you how. So let's say, okay, I've got a velocity versus time graph that looks like this. Right? If I wanted to calculate the displacement off of that graph, what do I need to calculate? Don't say displacement, I already said that. But what do you need to calculate above the graph? Spencer, you just like
The area?
the area under the line. Okay? If I calculate the area under the line, then I'm going to have the displacement of this object. Okay, and this is what we did at the end of the day yesterday. Okay, we did a couple of examples of this. Okay, if I want to calculate the area, I'm going to have a triangle on top of a rectangle. Okay, well, this rectangle, if I calculate its area, I'm taking the time in seconds and multiplying it by my initial velocity. In other words, this is VI times t. Okay, which is the first part of this formula that sets up to calculate displacement. Right? The other part of that formula, the 1/2 AT squared, okay, calculates that. Half the base times the height also works, but okay, this does the same thing. 1/2 AT squared gets you the triangle. Okay, everybody all right with that? So by adding those two together, do I get displacement? And that's what that formula does, calculates displacement. Now, this one right here looks very similar, except it uses VF and subtracts the AT squared. Okay, so what is that one doing? It's taking VF, that would be this value here, and multiplying it by time. In other words, it's calculating this whole square. And then it's subtracting 1/2 AT squared. Well, in this rectangle right here, is this triangle here and this triangle here, are they the same? So if I calculate the area of this box by going VF times T, and then I subtract this triangle, does that leave me with this area? It does. Okay? So those two equations are calculating the area under the line on a velocity versus time graph. They just do it way quicker than having to actually draw the shapes and calculate their areas. Okay? Everybody all right with that? Okay. This one here, this one comes in very, very handy when we're doing projectile motion, because it doesn't need time. It's got acceleration, the two velocities, and distance. Okay, so it's very, very useful if we're dealing with like how high something will go. Okay, and that always happens halfway through its flight, so I don't always know how long it takes to get there. Okay, but I know how high it is off the ground, or I know its acceleration, or something like that. So it's a handy formula because it doesn't involve time. Okay, and then there's this last one. It's the one we use the least. Okay, and that's because the acceleration has to be uniform for it to work. That means it has to be a graph that looks like this one. It can't be a graph that looks like this. Okay, that's not going to work for this. Okay, so really what it does is it says distance is final velocity plus initial velocity divided by 2. Is that like, if I had a graph that looked like this, would that be the height of the triangle? It would be. So this formula is really just this. It's really just average velocity times time. It's really just v equals d over t. Okay? So we don't use it that often because we don't like to use v equals d over t for an object whose velocity is actually changing, because it kind of implies it's not. Okay? All right, questions so far? Okay, so what we're going to do is we're going to work through examples of each one of the formulas. Okay, we'll look at how we manipulate each formula, okay, all of that kind of stuff, and then we'll kind of do some examples. Okay, I'm going to have you write this one down, okay, in your notes, or just take a picture of it and insert it into your notes, whichever. Okay, and then write down your givens for it. Okay, give you a minute here to get that done. Okay, so in this question here, they're telling us that we've got this hybrid car that has an initial velocity of 10 meters per second east. So they just told me VI is 10 meters per second east. Okay? It accelerates at 3.0 meters per second squared east. What did they give me there? Which variable did they give me? Acceleration. Okay. How long will it take the car to acquire a final velocity, they're telling me VF, of 25.0 meters per second east, okay? And they want to know how long. So they're asking me to find time. Okay? How important is it for me to be able to read a question and get that information from it? Very important. Okay? There's some things you can do that can help you identify what variable is which. Units is one of them. Okay? Any number in meters per second is either a speed or a velocity. Okay? And you can tell if it's got a vector whether it's a speed or a velocity. Anything in meters per second squared is an acceleration. And anything that's in seconds, minutes, or hours is obviously a time. Okay? But there's also contextual clues sometimes that are in a question that we have to get. Okay? In this case, it's telling me that it is not starting at rest, that it is in fact accelerating in a positive direction. Those are things I have to get kind of from the story. Okay? So there's a little bit of reading comp almost that has to go on when you're doing problem solving in physics. Okay? And it gets more involved. This is about as simple as it gets. Okay? You get to physics 30, we've seen things on the diploma exam, questions on the diploma exam that require people to read an entire page of text to answer one question. Okay? So being able to kind of glean the little pieces of information out of that one page of text is pretty important, because not everything in that one page of text matters. Okay? But some of it's contextual, that's things the story tells you, and some of it is numerical. What are some measured values that this question wants me to use? Okay. All right, so I got to find time. What formula am I going to use here? Exactly. Okay, this is the one that matches the values given to me in the question. Right now, it isn't set up to solve for time, but that's okay, because I can do algebra. I can make it solve for time. Okay? All right, so if you're getting a question like this just on like a quiz or a test, just so you know, I would give you a mark for your givens, just like I did on today's quiz. Right? I would give you a mark for identifying which formula needs to be used. Okay? If there's algebra involved, then I give you a mark for the algebra. In this case, there is some algebra. I want to solve for t. Right now, it's on the bottom of the equation. I need it on the top, so what do I have to do with it? Saw a couple people do this. Okay, yeah, I need to move it to the other side of the equation. Right now, I'm dividing by t. If I want to move it, I'm going to. Chris just did this. I assume that doesn't mean that this was out of bounds, but that multiply, right? Okay. Okay. So I'm going to multiply both sides by t. Now t is over here. All right. I want t by itself, so what do I have to do with a? Divide it over to the other side. Okay, so now I know that t equals Vf minus Vi over A. So you'd get a mark for that. Right? Sometimes I even give a mark for the next step, which is putting in the numbers. Sometimes, not always. Okay? So we would have 25 minus 10 divided by 3. Okay? Sometimes you get a mark for that. And then obviously you would get a mark for your final answer. 25 minus 10 is 15. 15 divided by 3 is 5. Okay, so we would be looking at that this will take 5.0 seconds because we have two significant digits. Okay, so that's supposed to be 10.0. Everybody all right with that one? Okay, you would have got questions like that in Science 10 for sure. All right. See if you can solve those two questions. Oh, sorry. One thing you're going to need to know. They're giving me a velocity in kilometers per hour, but they're giving me the acceleration in meters per second squared. What do I have to do with this kilometers per hour? I got to convert it to meters per second. Okay, how do I do that? Okay, so that means I've got to convert two different units. I got to convert the kilometers to meters. How do I do that? I multiply by 1,000. There's 1,000 meters in a kilometer, so I multiply by 1,000. Okay, and how many seconds in an hour? 3,600. 60 minutes in an hour. 60 seconds in each minute. 60 times 60 is 3,600. Okay, so we got t equals, okay, we know t is 9.3 seconds. Okay, we know that our v is 20 kilometers per hour. Okay, so here's how I convert that. I write it like this, kilometers over hours. And then I multiply by my conversion factors. Okay, in 1 kilometer, there are 1,000 meters. Okay, now I've got a kilometers on the top and a kilometers on the bottom. Okay, and they're going to go away. And I know that in 1 hour, there are 3,600 seconds. We got an hours on the top and an hours on the bottom. Okay, so basically what this equation is telling me is go 20 times 1,000 over 3,600. There's a shortcut, and you'll probably just memorize it, and that's probably not a bad idea. If I just look at this part of this equation, is that the same as just dividing by 3.6? If I multiply something by 1,000 and then divide by 3,600, could I have just saved a lot of time and divided by 3.6? There's your conversion factor. You can convert kilometers per hour to meters per second the long way, or you can just remember that you just have to divide it by 3.6. Okay, which is probably what you will do. Okay. All right, I'll give you a few minutes on those, and then we'll look through them together here. Okay, so for number one, they give us a motorcycle with an initial velocity of 6 meters per second east. Okay, and it accelerates at 4 meters per second squared. So that's A, east. Okay, how long will it take? How long is always time, so that's what I'm looking for, to reach a final velocity of 36 meters per second east. Okay, everything's east. Do I need to worry about positives and negatives? Everything's positive, right? It's all east, so I don't have to worry about that. Okay, so I'm looking for time. The only formula I have that has the givens I'm given is this one. All right, so it's exactly the same one we just did a minute ago. Right, we're solving for time, so we would multiply both sides by time, and then divide both sides by acceleration, and plug in our numbers. So that'll be 36 minus 6, okay, divided by 4. Okay. So what's 30 divided by 4? 7.5. That'll take 7.5 seconds. That has 2 significant digits because both of those numbers have 2 significant digits. Okay, everybody all right with that one? Okay, how many people have done the second one? Okay, let's look at the second one. So on the second one, the only thing that's different is that we have to convert the 20 kilometers per hour to meters per second, and then at the end, we got to convert our answer back to kilometers per hour. Okay, so my initial velocity, they told me, is 20 kilometers per hour. I need to divide that by 3.6, okay, to get my meters per second. So 5.5. And that is north. Okay, and then it accelerates at 1.5 meters per second squared north. Okay, for 9.3 seconds. What did they give me there? Time. What is its maximum, or in other words, final velocity? Okay, so this one wants me to calculate VF. Okay, so am I still using the same formula? Yep. Okay, so A equals VF minus VI over T, and I want to get VF by itself. So according to our rules of algebra, what should I move first? Time. Time is not attached to VF. This is where we would use that third rule. Okay, so I would multiply both sides by T, and then what do I do with VI? Add it to the other side. Okay, here's just something to think about if you're trying to make this make sense kind of logically in your head. T times A equals the change in velocity. That's what this side is now calculating. VF minus VI is the change in velocity. So if I take VI and I add it over here, my formula is saying take the initial velocity, add the change in velocity, and you'll get the final velocity. Well, logically, that makes sense. Okay? If I go to work in the morning with no money, and I work for 8 hours, and I make, I don't know, $100, okay? That the change in money is $100. My final money is $100. I added the change to my initial amount of money and got my final amount of money. Okay? Everybody kind of follow me on that? Okay? All right. So now I can plug in my numbers. So I would have my 5.56, okay, plus 9.3 times 1.5. Okay. So if I punch that into my calculator, I'm going to use all of this. In terms of significant digits, always keep all your decimals until the very end. Don't round anything off until you're at the last step. Okay? So take that, and I'm going to add that to 9.3 times 1.5. Okay, so my final velocity is 19.5 meters per second, but they wanted it in kilometers per hour. So I would multiply now by 3, not by 3,600, but by 3.6. two significant digits, 70 kilometers per hour north. Okay? Everybody with me on that? Okay, there's one manipulation of that formula we didn't go through, and I just want to cover that really quickly here. What if I want to solve for VI? What if I want to solve for VI? What should I move first? Time. I should still move time first, okay? It's not attached to VI, right? So I've multiplied both sides by time. Okay, now I want to get VI by itself. I've got two options here. Okay, one of them is to move VF over to this side to isolate VI. I can do that, but what do I need to remember about VI? It's negative. I never do it that way. Okay, the reason I never do it that way is because I always forget that I left a negative value on the other side. And so when I'm done the question and I get north, I have to remember that it isn't north, it's negative north, which is south. Okay? And I never remember that. All right, so what I do instead, okay, so you could totally go subtract VF and leave this and get negative VI, but what I do is I actually add VI over here. Okay, and you're probably going, how does that help you, Codere? You're trying to solve for that. You just moved it over on the other side with a bunch of other crap. Okay? Yes, I did. But can I now take this whole thing and move it over there? By doing what? Subtracting it. Okay, think order of operations. Would I multiply those two numbers together before I add it to this? I would. That means it's really just one number. It's like x. So I can just subtract x over the other side. Okay, so here's what I've got then. I have VI equals VF minus T times A. Let's think back to the logic we did a minute ago. I take my final velocity and I subtract the change in velocity. That should give me my initial velocity. Okay? If I have $150 at the end of the day and only made $100 at work, what did I start the day with? And if I end the day with $150 and I made $100 during the day, how much did I start the day with? 50 bucks. Okay, you went 150 minus the change in money to get what you started the day with. We're doing the same thing here. Okay? All right, so that's the other manipulation. It's totally up to you which one you do. Okay? Just know that if you leave VI negative, that you have to remember you did that for vector purposes. Okay? All right. I want you to copy that one down, write down your givens, and see which formula we should use. We'll see if we get further than that or not. Okay, so on this question here, okay, we have a cattle train traveling west at 16 meters per second. It's brought to rest in 8 seconds. Right? This is a question that's a bit more contextual. It's not saying outright, this one's VI, this one's VF, and this one's time. Okay? It's not outright doing all that like some of the other ones did. Right? So what does this question in fact give me? It gives me VF. What's VF? 0. It's brought to rest. That means at the end it's stopped. So I know that VF is 0 meters per second. Okay, that's it. That one was a contextual given. Okay? They never outright said VF is 0. All right, what else do they give me? VI, what's VI? 16 meters per second west. Okay, and it does that while coming to, it does that in 8 seconds. So seconds is always time. All right, 8.0 seconds. And they want to know what's the displacement of the cattle train in coming to a stop. So I'm looking for D. So I've got an object that's accelerating, and I'm not given the acceleration. Do I need it? I don't. I mean, I could do this in 2 steps, but I don't need to. I have a formula to do it in 1, which we'll talk about tomorrow. Okay.